So in the last video we discussed the equilibrium condition. So the equilibrium condition, we developed three equilibrium equations for the x, y, and z directions for a stress element, and we said that those equilibrium conditions need to be true in order for the element to remain in static equilibrium. So in this video we're going to talk about the second necessary condition for a given state of stress to be valid, is that it has to be compatible, which means that it has to have a piecewise continuous displacement distribution. So u of x of y and v of x of y and then 3D w of x of y need to be piecewise and continuous. Um, so, so what this piecewise and continuous really means is that two things really need to be in play. First is that the boundary conditions must be valid for the given deformation distribution. So if you have a boundary, like in the case of a fixed plate or a pinned connection or a roller connection, those boundary conditions must be valid. And the second is there can be no overlapping holes or points. So for example, if you had a part of your rigid body that had 4 points A, B, C, D, and within that those 4 points you had another point E, and that rigid body underwent some external stress, or had some external forces being applied to it, and that caused deformation within your rigid body. So it ends up being this new state of deformation. All right, and then after that deformation, you had some point, which I'm going to call E prime, which was originally inside the other 4 points, was now located outside. This would be a version of something that would be considered an overlapping point. All right. So this would be an invalid case. All right. For it to be a true valid case, the point E prime would have to be within the original boundaries it was in the undeformed state. So it has to be within A prime, B prime, C prime, and D prime. Okay. So this condition where you have to have a continuous distribution, we can define using our strain definitions. So we have our first strain definition of being epsilon x du dx. So if we take the derivative of this equation of epsilon x 2 times with respect to y, what we end up getting is we get d squared d cubed u of x of y dx dy squared. All right. So if we can repeat this process for epsilon y and gamma xy, if we do that, so we're going to take the derivative of epsilon y with respect to x squared. If we do that, we get the third derivative of v of xy dy with respect to x squared, and we can do the same thing for gamma xy, but we're going to take the derivative one time with respect to dx and one time with respect to y. And if we do that, we get the third derivative of u dx dy squared plus the third derivative of v with respect to dy dx squared. So what you'll notice is on the right hand side of our last equilibrium equation is that there are two terms here. The first term, the third derivative of u dx dy squared, is the same as the equation in the top left for the second derivative of e of x of epsilon x with respect to y. So we can substitute that in here. And then if we look at the second term, the third derivative of v with respect to y and with respect to x twice is the same as the left-hand side of this equation, so we can plug that in here. And this gives us our first compatibility equation here, which is the only equation that's necessary for a 2D compatibility. So if you have a 2D strain field, you only need this first equation to ensure that the strain field is compatible. If you have a 3D strain field, using a similar process, you could develop the following additional compatibility equations, and you would need all of these would be necessary for 3D cases. Okay? So we're going to go on, and I just want to explain to you how you would use these compatibility equations, or why you would use these compatibility equations. So we know in chapter 1 we talked about if you were given a displacement function, u of x of y and v of x of y, we showed how you can determine epsilon x, epsilon y, and gamma xy. We also know that if you have the strains are known, so if you have epsilon x, epsilon y, and gamma xy, we can then determine the displacements. All right. So let's say we have that secondary case. So let's assume that we have some strain field that's defined like this. We have epsilon x, epsilon y, and gamma xy. So we can then, so the first thing we can do is we can find u of xy by integrating the epsilon x equation, or should we integrate with respect to d of x. So if we do that, it's a partial integral. So we're going to end up getting x of y plus f of y. All right. We can repeat this process for the second equation here to solve for v of xy. So we can say v of xy would be equal to the partial integral of y with respect to y. If we do that partial integral, we get y squared over 2 plus g of x. All right, and then so then if we use the third equation, all right, we could say that we know that gamma x of y was given to us as being equal to xy, which we know is equal to dv dx plus du dy. We can rearrange this equation, right, and we can set du dy equal to x gamma xy minus dv dx. All right, and we can plug in our known value of gamma xy as xy minus dv dx. All right, so if we integrate this equation with respect to if we integrate the right hand side of this if we integrate this equation with respect to y, we can get u of xy, right, is going to be equal to x y squared over 2 minus, if we plug in our value, dv dx is going to be equal to 0 plus g prime of x. So if we integrate that with respect to x, what we'll end up getting, or with respect to y, is we'll get minus g prime of x y plus some unknown function h of x. All right. So from these equations, what we notice is that we actually have two equations for u of xy. All right, so we have two possible displacement fields. Our first possible displacement field we got from our first integration, and then our second possible displacement field we got from our gamma xy definition. So the issue is you can't have, if you have one set of external forces acting on a rigid body, you can't have two possible displacement fields. There's only one valid true displacement field. So using our compatibility equations, we can then determine the unique solution for displacement fields. So from this, we will get one displacement field for a given strain field, and then for a given loading there must be only one correct, unique solution. Alright, so in the next examples we're going to go through how we can use the compatibility equations to determine the true unique solution for our displacement fields u of x of y and v of x of y.